Welcome everyone to the last session of the meeting. In this session, we have three very interesting talks by Kornilov, Dr. Biswas, and Dr. Hanus. I remember you as the speakers that they have 25 minutes for the talk and 5 minutes per questions. And as you may know from the last day, if you have a question, just type it in the questions and ask box. So with this, I welcome the first speaker of the session, who is Kornilov from Max Born Institute, and he will deliver a talk entitled Relaxation at Complex Resonances Studied by Wavelength Selected XUV Pulses. Oleg, please, the virtual stage is yours.
Thank you very much, Rocio. Hello, everybody. I will share my presentation first. So let's see. I hope you can see that. Okay, so as Rocio said, my name is Oleg Kornilov, and I work at Max Born Institute in Berlin. Today, my talk is titled Relaxation at Complex Resonances Studied with the Wavelength Selected XUV Pulses. And the topic of this talk is not so much about the attosecond dynamics at attosecond resolution, but very much along the lines of the research which was yesterday presented by Matteo Lucchini. The femtosecond XUV research in kind of support and complementary to the research done at the attosecond timescales. We also have the similar implementation of the technique as Matteo showed. In fact, we worked together with the same collaborators, with the Luca Poletto and his team from Padova, and build a similar device. I will not go so much in the technical details today, but rather present you a few scientific cases which we have studied and try to motivate the joint sort of research program, and try to motivate you that this is also an important area of research which can be extended into the attosecond regime. So what I mean when I talk about relaxation at complex resonances is something which I guess should be pretty obvious. We in time domain would like to look at certain features, maybe in spectroscopic sense, which are complex to be understood in spectroscopic static methods, and which then necessarily actually have some dynamics related to them. We'll go maybe to the simple cartoon of a simple resonance, so something which may say we understand. This is the typical picture of a Fano resonance where we have a discrete state which is buried in the continuum of states, and the excitation pulse, let's say, or photon can excite both of these. In such a situation, we get the infamous Fano absorption profile in our spectrogram of such a process, which has been explained already in 30s, but formalized by Fano in 60s, and which basically describes the interference between the transition to the continuum channel and transition into the discrete state. However, so this was actually very nicely described in the talk of Thomas Pfeiffer yesterday. However, what happens if this picture is a little bit more complicated? And by more complicated, I mean here just one step forward. What if we have two discrete resonances coupled to the same continuum? Well, that work has also been done. This system has been studied in many cases. And I want to say that actually this system already presents the first little step towards real time domain, because the Fano resonance, if you have a single Fano resonance and you can measure the spectral shape of it, you can predict everything. You know everything just from a spectral shape, because the phase and amplitude properties of spectra are connected for such a situation. However, when you have double resonance, things get complicated. This problem has been studied many times, but one of the most interesting research directions was studying the laser-induced continuum structures, so basically where these resonances are induced by lasers. And what was described and can be obtained quite trivially, when you have the lifetimes of these resonances, or width of this corresponding spectral features overlapping, you cannot anymore consider them as decoupled discrete states. They are coupled through the continuum interaction. Essentially, you could think if these are electronic resonances about electrons, jumping in and out. And in such a situation, you have to rewrite your problem, and you arrive to a very interesting and somewhat counterintuitive result that you have a constructively and destructively interference cases. One of these resonances will become very broad, this guy, and so correspondingly short-lived, and one will be very, very narrow. And the stronger the coupling means the shorter the lifetime, supposed lifetime of the original discrete states, the longer this lives. This is called interference stabilization in the research of 90s and 2000s, and has also been discovered in several other cases. Was called, for example, in this paper, interference narrowing. So I would say here already we could see that time domain tools can actually help us a lot, because we can in time domain see the short and the long-lived states, while in the spectral domain we may not be able, for example, to see that one, since it will be very, very broad. We can also go further and look at the theory of what happens if we have many, many, many states. And in the chemical context, that problem has also been considered, and people arrived at very nice results. Also, Francois and Michael, who joins this workshop, has done contributions to that. The first time it was considered by Pavlov Verovkin. Here, the situation can be solved analytically when you have an n state coupled to a single continuum, and what you will observe, if this coupling is very strong, that you will have a separation of timescales. A few of the decays will happen very quickly, and a large portion of them will be delayed. And the stronger the coupling, or the larger the number of states, the longer will be this delay. This is kind of corresponds to trapping of the populations, a purely quantum mechanical trapping. It was proposed in several different contexts. And as you will see in my talk, we propose that this actually also may have something to do with the relaxation of the pH molecules, of which Frank Lepine was talking about. We have, in fact, a joint work with him on naphthalene, where we looked a little bit at a different angle with a different tool at the molecule, which he beautifully studied in his lab, and have observed something reminding that. I'll get to that soon. Now, these are all still rather model systems, and the question arises how general this phenomenon is. Of course, we don't really know, but there is an indication that this can be even more general than these electronic excitations, discrete excitations. And here I would like to refer to the recent work of Gellin and co-workers, where they looked at the coupling of the conical intersection to a bath of states. So they've designed a model situation where they have two nuclear coordinates with a conical intersection. So that is already a relatively realistic large molecule example. And they've been able to show that a phenomenon similar to this trapping I just mentioned may happen also in these model situations. In fact, this red curve, which I have copied from their paper, corresponds to an intermediate coupling strength. So what that means is that if you have a weakly coupled, bath-coupled conical intersection, and you observe, as often happens, the coherent dynamics of a molecule relaxing through that model conical intersection, at weak couplings and strong couplings, the decay will be relatively fast. But if you introduce some magic coupling, then that coherence lifetime becomes longer. In fact, the oscillations, the coherent oscillations become decoupled or trapped at the conical intersection. In fact, similar results have been recently demonstrated in a very different way, but also about conical intersection by people from Max Born Institute, by Benjamin Fingerhut. So our goal was and is to try to support all these interesting purely time domain phenomena and try to find them in maybe different molecules, doing the experiments with their XUV pulses, pump probe experiments with XUV pulses, and using our monochromator. So that roughly gives an outline of my talk. What we wanted to look at are complex resonances, and those you can find either in the highly excited small molecules, where you can achieve high electronic density because the energy is high. And in this case, you often use XUV as a pump. This would be the case of nitrogen and naphthalene. Or you can actually also see that in large molecules at low excitations, where the vibronic states play the role of density, and you hope to see some of the quantum mechanical phenomena like this trapping at the conical intersection. Here, XUV would be as a probe. So I'm going to go through the examples one by one briefly. So the smallest, before going to that, I will briefly present our experimental setup. I don't have to go into the detail. As I mentioned, the setup is basically similar to the one designed by Luca Poletto for the people in Milan, the one which Matteo Lucchini was talking about. We have a two-stage time compensating monochromator where we select the harmonic we would like to use on the first grating. The pulse front is tilted, and so we compensate that by selecting the same harmonic by the second stage in the mirror configuration, thus compressing the pulses. We have a pump beam where we could use infrared pulses or 400 nanometer pulses, or in fact also we have the tunable sources, and we can perform this way pump probe experiments with wavelength select X UV pulses, either as a pump or as a probe. Cross correlations we can achieve by about 35 femtoseconds, and the spectral resolution is better than 500 milli eV, can be even better. Transmission is also pretty good. So that is a typical set of parameters we could use. So now going to the nitrogen molecule, I would like to show you a research we've done on photoelectron spectroscopy at one of the autoionizing resonances of nitrogen. So going a little bit more to the molecular context, not this just lines, but real potential energy surfaces. This is the model of the potential energy surfaces for nitrogen. This is the neutral molecule X state. This is what you ionize. And then in the ion, you can have predominantly 3 electronic states, X, A, and B. Of course, each of these states has the sequence of Rydberg states connected to it. We are, in this case, talking to a Rydberg series converging to the B ionic state. This is the one which is populated by our harmonic, which we select at about 17 eV. And then this Rydberg state is an autoionizing state, so it will autoionize, kicking out an electron and delivering the ion either in the X or A states. These would be our 2 continua, which we are talking about. And with our infrared pulse, we can ionize at autoionizing states before autoionization happens and get an additional feature. The energy of the electron would be shown by this arrow. In fact, this is exactly what we see. This is the XUV only image, and this is the difference image when we add the infrared light, and we can see the appearance of this very strong feature close to the center. This is exactly the ionization of the Rydberg electron before autoionization takes place. We observe that feature only very close to the time overlap. Its lifetime is very short, corresponding to the known lifetime of the resonance. This is a particular window, so-called Hopfield windows series resonance. In nitrogen, thanks to our monochromator, we can select only that and be sure that we study exactly this system. So what do we observe in that case? Long story short, we have extracted not only the intensities of these electrons we detect, but also the angular distributions, and found out that the angular distributions change over time. So here you see the typical asymmetry parameter beta 2, beta 4, and you could see that the value of this beta 2 grows over time window of our experiment, which corresponds to the more peaked distribution of electrons. Now, if you would think about it, if you have a single state which decays, you would not expect the angular distribution to change. The state is a state, it stays the same. So what must be happening is that you have actually 2 states. And in fact, their decay times have to be vastly different. What is interesting is that when you use quantum defect theory to predict the lifetime of these states, this was known that there are 2 Rydberg states overlapping in that window series. You actually predict that their lifetimes have to be the same. However, in the framework of the theory of the quantum defect theory, of the general quantum defect theory, in fact, you are not taking into account exactly this effect of the coupling of the 2 exit channels through the continuum. And so we have cranked up a very simple model where we put on top of that results, which are well established from 80s, the coupling, so-called interference stabilization. We had to look a little bit deeper because in the original works, we always looked at so-called balanced case, where basically you can say there's only one continuum. And in the case of nitrogen, you have minimum of 2 continua, in fact more. We will a little bit extended this system. It's not very difficult, and discovered that basically even when you have different couplings here, you could still have stabilization, although if the balancing between different continua becomes and states becomes non-equal, then this stabilization will be temporarily. This is the effective coupling parameter, and you will have this minimum of this band corresponds to the long lifetime. And so actually numerically using this theory, we propose that in fact one can say we observe that stabilization in the molecule. Of course, that is all a function of what kind of basis you use to describe your electronic states, but in that more traditional basis of quantum effect theory, we would have to put that on top. And we see that's experimentally in angular distributions. Now, switching the gears, we can look at more complex molecules. This in case naphthalene. You have seen these type of graphs from Frank Lepin's talk on Wednesday, where he looked at a beautiful series of pH molecules. With him, we only collaborated on that one with our postdoc Gerd, and we've done the photoion experiment, not the photoelectron experiment as presented by Frank recently. Photoion experiment has its drawbacks, but we used a little bit different advantage of our setup that we can set different Forden energies. So these arrows correspond to the harmonics we choose, and we can ionize the molecule with more and more Forden energy, correspondingly grabbing higher and higher density of states, these shake-up states or these correlated states, as Frank discussed. And very similar to what Frank sees in his lineup of molecules, as he shows the bigger the molecule, the slower the decay. Here we see also that the higher the Forden energy, so the larger the bandwidth of states we can reach with our Fordens, the longer the decay. The decays we measure similar like Frank by using the infrared light and ionizing the ion twice. So we have a dication, which we can distinguish in our ion mass spectrum. And we propose, of course, our research, our results at the moment do not give the definite result here, but we propose that this increase may be explained, and also in connection with Frank's result, may be explained by this bottleneck effect, which I described on my first introductory slides. Basically, the picture you would have to look at is the higher the number of the density of states you excite, the longer they will stay trapped if, and only if, they all have to go through the same channel. So they have to have a small number of decay channels. In this case, the assumption is that there is a conical intersection towards the ground state and that this serves as a bottleneck. They basically destructively interfere there and cannot really relax all of them at the same time, as long as this is only one channel. If there will be a large number of dissociation channels, that effect would not be observed. Of course, very interesting result would be appearing from the more at the second type resolution research, where you would try to see this prompt portion. So basically you would see that there's a separation between the timescales of relaxation, with a few states relaxing extremely fast. In our estimates, that would be some femtosecond, and the rest relaxing on the timescales of this 30 to 40 femtoseconds like observed. However, at the moment, for our setup, this is beyond our capabilities. So that would be very interesting direction of research. So now I would like to move on to a slightly different type of molecules, of objects we want to study, namely to the larger molecules. This is a slightly different program which we implement in our laboratory. We would really like to look at molecules which are too big to fly and therefore have to be located in some kind of solvent. We would also like to pursue the solvent interaction with some ideas of maybe going and looking at these effects of the bath coupling on the conical intersections. We're not that far yet. We at the moment are establishing the techniques and getting the first spectra and basically starting to understand that this method actually does work, the photoelectron spectroscopy in liquid phase. And so for me, that would be now the topic I would like to describe you. So in our experimental setup, we have used the end station, which I think is similar to what Hans-Jakob Werner presented in his talk yesterday. This is a liquid jet coupled to the magnetic bottle time-of-flight spectrometer. We sent 2 pulses into the interaction region, and we detect the photoelectrons in the pump probe configuration. Unlike Hans-Jakob, we are concentrating on the solutions, so we're not really studying the pure water. We are putting the organic molecules in, and we try to establish the photoelectron spectroscopy of organic molecules at solution at low concentrations, which are typical of all the femtochemistry research. But now with the photoelectron spectroscopy, which gives us the advantage that we could measure the binding energies of the molecules and the transient binding energies, and thus we can actually follow the relaxation through the conical intersection, and in principle also down to the ground state, or the ground state of the isomer. So I would like to show you a couple of results which we have been able to achieve so far. The molecules we looked at so far are called yellow dyes, because these are very simple molecules which absorb at 400 nanometers, which are very cheap and have good solubilities. One of them is this Quinoline yellow, because the molecule is not so popular among femtochemists. Mostly you find the literature in the food chemistry journals, but there was one investigation of transient absorption spectroscopy of that molecule. This is the structure here. We've been able to detect its static photoelectron spectrum. You could see that these measurements are rather tedious, because this spectrum is a spectrum of liquid water. And somewhere here on the flank, because the molecule has a lower IP, you could detect the molecular signals. However, the advantage is that playing some tricks, we could get this background free. So although the signals are pretty low, there's no background, and we could detect pretty nice electronic structure. Of course, washed out for solvent interaction, as typical for solid molecules. Then we went on and actually studied the relaxation, time resolved relaxation of that molecule. This map represents such a result. Here you could see the binding energy scale and the time scale, which is more or less logarithmic. It was much easier, much more convenient for us to measure like this, and actually presenting as well is also nicer. And here you could see below the noisy region, this is where the ground state used to be. We subtracted it, and on the top is the new red signal. This is positive signal, is the excited state, which decays and also experiences some spectral shift. When we look at the decay of this feature, we could see the timescales of 1.3 and 90 picoseconds. And in fact, these timescales are kind of very close to the results of the work of Han et al., who have studied this looking at transient absorption. And they hypothesized or kind of suggested that what is happening there is that there is the excited state intermolecular proton transfer. So this proton is jumping from nitrogen side to the oxygen side in the first picosecond time scale. So apparently it's tunneling because it's relatively slow, but then the molecule starts rotating and goes back to its trans amino isomer, this guy, because we know that it's a light fast molecule, so isomerization is actually pretty probable for it, and the proton moves back. So we think that this is exactly what we see. We see 2 time scales, and the cross-section for ionization, this excited state changes when the proton moves, and then we see the loss of population. The excited state as it goes to the ground state. This is all in the solution for molecules with a concentration of just 2 or 3 millimolar. So I think that's a nice technical achievement here. Of course, we are not yet sure about this interpretation because we do it in water, and we should be worried about the H bonds which are formed. So further research is needed to actually establish that this picture is correct for that molecule. For the effect,
Oleg, you have 1 minute left.
Yeah, I am almost.
Okay.
Another effect we observed is the spectral shift in the beginning, which goes without loss of population. And we suggest that this may reflect the reorientation of the solvent molecules upon excitation. If the dipole of the molecule rotates upon excitation, then the solvent molecules in water have to reorient themselves. It's very well established that water is extremely fast solvent, and this happens very quickly. That should correspond to the stabilization of the energy of the excited state, and that would be what we see here. And as just last peek into what we do, we've also looked at many other molecules, and among them aminoazobenzenes. These are azobenzenes with the amino groups. We've been able to measure the static spectra of them, and maybe just as an advertisement, very, very recently now, we've basically been able to collaborate with the beautiful people, Evgeny Titov and Roland Mitrich, who managed to crank up a very heavy calculation, TD-DFT calculation with the surface hopping, which provides a very nice, in my opinion, correspondence to our measurements. You should appreciate that the binding energies in their calculations are not adjusted here. They really get the binding energies here. I evaluate the maps similar to the experiment and compare them. You could see the binding energy like this line and this line is very similar. And we also see similar decay time scales. So I think this research program goes very well, and hopefully we'll soon be looking at those very exciting quantum mechanical phenomena at conical intersection. So I'll skip the summary because I would really like to acknowledge people involved in this work. And it is, first of all, of course, the team at MBI, Evgeny Kornilov and Nicola Meyer and Johan Umert, Martin Eckstein and Gerd Retzmar, who were over the years responsible for that. But also, of course, my collaborators, Frank from Lyon and Giuseppe from Freiburg. And we have now very exciting collaboration with Stefan Hake on molecular switches, which I hope will deliver very interesting results. And of course, also Luca for helping us with the monochromator, and Roland and Evgeny for helping us with the theory. Funding was from MBI and TFG. And with that, I thank you for your attention.
So thank you very much. Now we have some time for questions. Let me check the chat. There is one question by Hans-Jakob Werner. So he says, thanks for the great talk, Oleg. Do you also add salt to your solutions to avoid electrokinetic charging? Do you see space charge effects?
So yes, Hans-Jakob, we do use salt exactly like you do. So we add anywhere between 30 millimolar, 60 millimolar solution. In fact, here at MBI, Andrea Lucchi has done some research on this topic, and we basically follow her advice. We did not play with that too much. The space charge effects we estimated. We do not think we see them. The effect has to be relatively small compared to the broadening due to other reasons. What we see is the pump-induced charge effect, and that we correct for in our maps.
Okay, there seems not to be any other questions. I will have a question instead. So in the last part of the talk, you talk about these aminoazobenzenes.
Yeah.
Maybe it was too quickly and I missed it. Which is the pump wavelength that you need for that?
They are also 400 nanometers. These are also yellow dyes. So we actually very much like molecules which absorb at 400 for obvious reasons. For experimentalists, it's very easy. You just take a second harmonic. And there's a huge range of dyes, which sometimes are very important, sometimes not important molecules, which give yellow colors. So these particular are very interesting also from a research point of view, because amino substitution, in the azobenzene, there is the pi star and n-pi star absorption. So there are two states. When the amino substitution benzenes, these come together. So this actually is exactly this complex resonance thing, although it's much, much more complex because it also is a big molecule and in a solution. But in principle, this is the merge of the two electronic states which takes place in those two molecules. So we had a particular interest in that, and I'm extremely excited that actually Evgeny managed to calculate this more or less correctly, it seems. So that's very interesting.
Very nice. So let me ask you a last question that has been posed by Fernando Martin. Do you think that it will be feasible to resolve in time the distinct decay of the interfering resonances in N2? In other words, could you use shorter pulses?
So I think you definitely can use shorter pulses. So for us, the problem was simplified because we chose the spectrum such that we cover only one resonance. However, this is not the most optimal time resolution you could get. In principle, you can afford a bandwidth which would be larger, not infinitely large, but larger than what we used. I think you could use up to maybe 0.5 eV, and therefore you can improve your resolution, maybe I would say to 3.2 femtoseconds.
So very nice. So with this, I thank you again for the nice talk. And I move on to the next speaker, who is Dr. Biswas from the Max Planck Institute for Quantum Optics in Garching. And he will present a talk with the title Probing Influence of Molecular Environment and Dynamic Polarization in Photoemission Delays. So, Shupavet, please, the virtual stage is now yours.
I am sorry, but we are unable to hear you at the moment. Can you please change the source of your audio? Thank you. We are still unable to hear you. You will have to take out the headphones.
Hello.
We can hear you now. Thank you.
Okay, sorry for this problem. Yeah, so maybe I'll start from the beginning then. Okay, so thanks to the organizers for giving me this opportunity to present our recent works on photoemission delay on molecules. So going back, starting with the basic definition of photoemission delay is the time interval between photon absorption and electron emission. It was actually predicted long time back in 1950s, where this Eisenbart, Wigner, and Smith predicted that if you take the energy derivative of the phase of the dipole matrix element of any ionization step, then you'll get this ionization delay. And though it is kind of predicted long back, it was first observed in 2010 in case of neon 2p2s delay. So what essentially it does is like it captures the local environment of the system from where the electron is emitted by this photoionization event. So subsequently, after this 2010 paper, there are works on different molecules and also solids and also numerous number of atoms. But recently, the molecular photoionization delay, this subject has been emerged quite a bit, and it gave lot of information in different directions. So if I take this first work by Hans Jakob Warner, where they measured the photoionization delay from N2O, and that gave the structural electronic structure, potential energy structure information, where their very large delay is kind of explained by the shape resonance, where the electron is trapped within the continuum, within a bound state within a continuum. because of the potential energy barrier in the potential energy landscape. Another significant work on this CO molecule, where people have measured the ionization delay from these two sites, one from the C site, one from the O site, and from that they could infer the initial electron wave packet localization, whether it's in the at the site of O or whether at the site of C. And very recent work, actually, yesterday Hans Jakob Werner also demonstrated this work, their beautiful work on liquid water, where they measured they actually compared the single water molecule with liquid molecules within the liquid, and they could measure significant delay between these two, and that gave essentially information about the scattering of the electrons within the molecule, within the liquid, and also effect of the solvation. So it's very clear that this technique of measuring ionization delay can give you the information about the local environment. So with that, in this talk, I'll explain two things. I'll try to explain two things, two questions essentially. First question is, what happens if an electron moves within the molecule? What is the, so this question is very much relevant to the chemistry. So in molecules, typically you have this functional groups, and electron can move around within this functional group, and it can experience the potential energy surface of this functional group. And this functional group essentially mainly steers or govern your chemical reaction. So it's very important to understand what is the potential energy structure, or what is the effect of this potential energy structure of this functional group on the propagation of this electron. On the second part, I'll deviate from this small molecule and go to the bigger molecule, and in bigger molecule you expect very high polarizability. And so the question is, when the light interacts with this large highly polarizable molecule, then what happens to the delay? What is the signature in the energy dependent delay for this highly polarizable targets? So in the first question, so molecular photoionization. So in a very crude picture, you can think of or visualize the photoionization from molecule as you first impinge your photon on the molecule, and you generate an electron, and that electron can subsequently propagate within the molecular potential, and then it comes out to the continuum. But the main difficulty is, in case of molecular photoionization, is to disentangle these two steps, because in case of, unlike atoms, in case of molecules, there are large number of states, very large number of states. Suppose for this CO molecule, CO plus ion, there are so many states, and it's sometimes very difficult to identify which is the from which state, electronic state, the electron is coming. So, but if you can distinguish these two steps, initial knockout and the subsequent propagation within the molecular potential, then what you can do, you can exclusively infer the delay caused by this functional group in different molecules, and in future people can do this measurement in a angle resolved way, and they can measure the photoemission delay in different angles, and with that you can do a three-dimensional map of the full potential energy surface. So with proper choice of the initial ionization step and with time resolved spectroscopy, this information can be obtained with this kind of delay measurement. So what we did is we chose a molecule which is called ethyl iodide. We tried to get the electrons from this 4D shell of the iodine atom, there is an advantage of that, actually a couple of advantages of that. First of all, this 4D shell is very deeply lying state. So it's hardly influenced by the molecular valence electrons. So your initial localization of the wave packet, electron wave packet, is kind of guaranteed. And then other than that, this 4D subcell has a giant dipole resonance. So you will get a very high cross section for your measurement, which is very good for your signal to noise ratio in your experience. Other than that, so in typical delay measurement experiments, you need a reference. So in our case, we used a neon 2p electrons as a reference, and neon 2p electrons and this iodine 4D resonance electron are very much separated in energy, so you can get a very good streaking traces, separated streaking traces. So what we essentially do is like we bombard the XUV attosecond pulse on this molecule, and because of this energy selection, we can selectively ionize the electrons from iodine 4D shell, and these electrons will go and interact with this molecular functional group or molecular environment or functional group potential energy surface, and then they will acquire information about that potential energy surface. And if you come up with another near infrared pulse, then you can get a streaking spectrogram, and this streaking spectrogram can capture all the time information of this electron emission. So how do you do in practice? So this experiment was done in collaboration with King Saudi University in Saudi Arabia. So we use a TISAP system, which delivers 25 frames per second near infrared pulses centered around 750 nanometer, and then we broaden this pulse with the holoco fiber, gas filled neon filled holoco fiber, and then subsequently we compress the pulse with chirp meters. With that, you can get a nice 4 frames per second to 4.5 frames per second pulse to drive your HHG. And with this HHG, you get a very broad spectrum with different harmonics, as well as the continuum part of the cutoffs part of the spectrum. And you, with your multi-layer meter, you select this spectrum in the cutoff region so that you can get isolated attosecond pulses. So this experiment was done in 2 photon energies at 80 eV and 93 eV. And the pulse bandwidth was 6.5 eV, which results in the duration of something like 260 attosecond. So with that, you do measure the streaked electron spectrum with the time of flight spectrometer, and you will get this kind of streaking spectrogram. So if I explain all the peaks, the main 2 peaks are ethyl iodide 4D peaks, 4D ionization electron peaks, and then as you are also inject the neon along with the ethyl iodide, you'll get a neon 2p peaks. And other than that, there will be a ethyl iodide homo peak also. So, but we are interested mostly on this ethyl iodide 4D and neon 2p streaking spectrogram. So with that, we used machine learning techniques to get this streaking lines, and from that, if you do a Fourier analysis, you can get the phase delay between these 2 lines. So this is actually explained here. There is a very small shift between this purple line and the blue line, and this is called the streaking delay. We did measure this streaking delay for several measurements for 2 energies, and we get the final delay values as like 50 attosecond for 80 eV and 18 or 20 attosecond for 93 eV. Then what we did is like we try to compare these values with simulations or some ab initio theory We use classical Wigner propagation method to compare this streaking delay measurements. The advantage of this method is it actually incorporates the IR, NIR field also, so you can directly compare with the experimental observation. Other than that, if you want to gauge this ionization delay, which is this EWS delay, you have to subtract the delay which is caused by this Coulomb laser coupling. So fortunately for these molecules, you can gauge this CLC term or the delay induced by Coulomb laser coupling analytically. And we subtract that and we get this EWS delay. And you can see that the main characteristics of this is at low energy, the delay is higher. And if you go to the higher energy, the delay is small. Now I'll put the attention of this blue line, which is the calculation for only iodine atom. So if you compare this two curves, one is this red point and this blue point, then you can see a very big difference between these two. This is also in streaking delay as well as in EWS delay. And so ethyl iodide has iodine, and that gives this red point. And only if you compare it with the only iodine atom, then this difference is essentially coming from the molecular part. But we actually wanted to investigate that when the electrons is coming from the iodine and it traverses or it traverses within the molecular potential or molecular environment, how much delay it occurs. And this difference is the delay that is kind of occurred by this propagation within the molecular potential. And there can be a very obvious question that how can you sure that this is not coming from the initial ionization step? The ionization step in iodine atom and the iodine molecule can be ethyl iodide molecule can be different. We actually tried to simulate that thing with the Wigner propagation theory, and we see that this is the plot for Wigner functions for iodine atom in bound state and ionized state, and also for ethyl iodide molecule for bound state and ionized state. And you can see that virtually these two are very much same. So bound state and bound state are both very much same. That means the 4D ionization, 4D shell is hardly affected by the valence electrons, and also the ionized state is also very much same. So whatever delay difference between ethyl iodine and iodine we saw is mainly coming from the propagation step, propagation within this functional group. So we could establish that delay. And we also this classical Wigner propagation theory also predicts something that if you take the bigger molecules or bigger molecules with iodine, maybe like the functional group is bigger, then you will expect angular distribution of this delay. So basically it means that you're in different directions of the electron emission within the molecular frame, the delay is different. And if somebody does angular resolved measurement with coincidence spectroscopy, something like this, and then they can measure this different angle differential streaking delay or EWS delay. Essentially what it can do is, like with this, it can map the full angular distribution of the molecular potential energy surface, which can be the ultimate goal for any chemistry, which means this can be very much important for like understanding the electron dynamics, ionization dynamics, as well as the steering different chemical reactions. So with that, I'll come to the collaboration part of this experiment and this study. So this is a big collaboration, mainly led by the MPQ and LMU people, led by Professor Matthias Kling. And this is the experiments are done in collaboration with King Saud University. And the machine learning analysis, we get the help from Professor Gregor Hartmann, and important theory collaborations led by Alexander Lanzmann, as well as this classical propagation theory was provided by Alexander Lanzmann, and the quantum version of the theory was provided by Hans-Joachim Werner. So with that, so you'll get this the details of this work in this original publication, which is recently published in Nature Physics. So with that, I'll come to the next part of the talk. So second part of the talk, like what happens if the light interacts with highly polarizable large target, a large molecular target. So we choose C60 as our target. It's quite a nice target in the sense. So its structural richness gives a lot of interesting features. So in C60, the carbon atoms are attached with each other by sp2 hybridization. So carbon has 4 electrons, valence electrons, and then out of that 4, 3 goes to form this sigma bonds. And there is one pi bond which makes this large pi electron cloud around this ionic cage, ionic C60 cage. So this gives very interesting features actually. So we always get interested in this collective excitation in C60, which is around 20 eV or 40 eV also. So it means this collective plasmon excitation means with this light, actually all the electrons together collectively, it interacts with the incoming perturbation. So we wanted to investigate what happens to the time resolve measurement or delay measurement when you come up with the photons around this collective excitation. So for this, we did the experiment in Milan with the group of Francesco Caligari. And in this case, the setup is, the technique is very similar. It's a streaking technique, but the setup or the method is a little bit different than the previous one. In this case, we come up with the usual 750 nanometer pulse, and after that it gets divided into the delay arm as well as the HHE arm. Before the HHE, higher harmonic generation, we do polarization gating, and because of that, the higher harmonic spectrum gets really broad and continuum, and you can see the higher harmonic generation spectrum, which we use in our experiment, is kind of extend from 20 eV or 17 eV to roughly about 40 eV. And in this case, we didn't do any kind of energy selection or spectral selection. We used the full spectrum to drive our streaking experiments or ionization, for the ionization of the C60. So for the C60, you cannot do, you cannot get in a gas form. It's a powder molecule. You can get in powder. So you need to use an oven, and this oven has to go up to like 550 degrees Celsius or 600 degrees Celsius to get a effusive jet of C60. So in the previous experiment, we could do neon as well as the ethyl iodide together, because the spectrally they are very much separated. But in this case, there will be a overlap, so we cannot do C60 and the neon experiment together. So in this case, what we did is like we used a shutter on this C60 oven, and with a very synchronized manner, we took the measurement for some time with C60 and for some time with neon. And this, eventually we saw that this strategy was very much important for delay measurement, or to stabilize, to have a stable interferometer.
Sorry,
so,
2 minutes left.
Okay. So with that, we took the streaking spectrograms, and with that, from the streaking spectrogram, we used the fitting procedure, and with this fitting procedure we get this phase between the neon and the C60, and from this phase you can get the streaking delay by dividing the angular frequency of the spectrum. And with that you get the final results, which is basically the delay difference between C60 and neon, and we did several measurements, and from that you get this final curve, delay curve, as a function of photon energy. Now, how do you understand this problem, this delay measurements? For that, you have to consider the first ionization step, XUV ionization step, and to understand that we used TD-LDA calculations, and in this model it gives cross section, and we considered 11 cross section for 11 states, as well as the EWS delay, the first ionization delay from this 11 states, same 11 states, and that goes into the model. And also in this case there is one more contribution which was not there, which was not important in the previous case, is the higher induced near field. So C60 has a very big electron cloud, pi electron cloud, delocalized, and because of this near infrared field, it induces oscillation in this full electron cloud, and that can give you some delay also. And to model that, we used the TDDFT near full distribution for C60. So if we explain this, it has a screening region within the C60, and then there is a dipolar tail in the near field distribution, and this near field distribution has to be added with the laser field when the electrons comes out in the continuum. So this model also takes the input for ground state electron density, as well as the polarizability of the polarizability at near infrared wavelength, and also XUV parameters and the NIR parameters. With that, we did classical trajectory Monte Carlo simulations, and we get this results. So this is the final result for our study, and this the work is still in progress, but to give you the preliminary hint, what we get is like we get this purple curve which is without any EWS, the initial ionization step, and also the without any near field. So what it does, it gives the information about the XUV chirp, and then if you add the near field distribution on top of that, you will get this YOLO curve. And on top of that, if you add the EWS contribution also, you'll get this rate curve. And you can see that it's very sure that the near field contribution is present in our experiment, as well as this experiment curve is kind of well matching with the contribution when you add the EWS. So in this experiment, actually, we probed two resonance. One is driven by the XUV field, which is this 20 eV plasmon resonance, as well as the near field generated by the near infrared field. So with that, this work is also conducted in a large collaboration, primarily by the MPQ LMU group and the DAISY group led by Francesca Caligari. And we have the theoretical collaborators from Himadri Chakraborty, who are from, and Maya, from whom we get the TD-DLDA, EWS, and cross-section data. And also we are looking for some new collaboration with the MPI Structural Dynamics Institute for new cross-section as well as EWS data for better understanding of the dynamics. So with that, I came to the conclusion. So in this talk, I essentially explained you two experiments as two studies. One which probed the molecular environment and demonstrate the influence of this molecular environment on the photoemission delay. And on the second part, I explained the time domain signature of this dynamic polarization and the effect of that thing on the delay measurement. With that, I personally thank the Marie Curie Foundation and the Alexander Hamel Foundation, and thank you for your attention.
So thank you very much for the nice talk. I'm afraid we are really run out of time, so there is just time for a very ultra fast question.
Okay.
So for the moment, I cannot see anything on the chat. Let's wait for a few seconds if someone writes something. Otherwise, you can just meet on the meeting hub or write a private message. Okay, so in that case, I thank you again, and then
okay, thank you.
Let's move to the next speaker. Oh, okay. So next speaker is Vaclav Hanus, and he will present a talk with the title of femtosecond snapshot of molecular wave packets and molecular ionization. So Vaclav, please, the stage is yours.
Okay, good afternoon. Thank you for the introduction. My name is Václav Hanus. I'm from Wigner Research Center for Physics in Hungary, and I will be presenting you a work which I did in Photonics Institute in TU Wien in Austria. And the title is Sub-femtosecond Snapshots of Molecular Wave Packets and Molecular Ionization. So when a laser pulse interacts with matter, several processes can happen. For example, there can be electronic excitation that leads to high harmonic generation. There can be population of Friedberg states. Obviously, there happens some ionization of atoms, which can be sequential ionization or non-sequential ionization. All these electronic properties, they in fact are very fast, and their time scales is on attosecond scales. And for this, there is already plenty of methods developed, like I can mention electron interferometry, electron momentum mapping, laser-induced electron diffraction, or high harmonic spectroscopy. Now, if this laser pulse interacts with a molecule, there are additional effects that happen, which are related to this molecular structure. There can be effects like nuclear rearrangements, or the molecule can, for example, dissociate. This dynamics is slower than the electronic dynamics. So this nuclear dynamics happen on scales of femtoseconds and or picoseconds. Typical method to probe this dynamics is using pump probe experiment, where you add the temporal resolution to this process by applying 2 pulses with certain delay. But the temporal resolution is limited by the duration of the pulses that you use in this experiment. So for example, for a Titan sapphire laser, this can go down to 4 femtoseconds. So now the question is, can we go beyond this limitation of the pulse duration? And can we observe this fast electronic dynamics together with the slow nuclear dynamics? To answer this question, I would like to present you a method or 2 methods, how you can get more insight into these 2 dynamics at the same time. So the first part of my talk, I call sub-femtosecond imaging of vibrational wave packets. And then in the second part, I will take a look what you can learn more about the ionization bursts in molecular double ionization. All these methods were recently published in following 2 articles. So let's start with the first part, with the some femtosecond tracing of molecular wave packets. So the interaction of a laser pulse with a molecule, you can visualize using this potential energy surfaces, where you have some certain pseudo coordinate, which can be, for example, the internuclear distance in a simple diatomic molecule. Then you have here the energy, and the electronic states are represented by these potential energy curves. During an interaction, when it happens to the ionization, the molecule can be excited to some certain electronic state, and this state can be subsequently probed, and the molecule gets to some final state, which you can detect in your experiment as, for example, fragments of these molecules. Now, this is a rather complex process, and many things can happen. Like the previous speaker mentioned, this picture can be quite complicated for more sophisticated molecules. So you can, there is plenty of questions that you want to learn about this process. You can ask, what is the ionization probability? You can ask, what will be the timing between the ionization steps? What is the final pathway that leads you to the final state? And what will happen? What will be the outcome of the interaction? And finally, what is the population of the vibrational states on the different electronic levels? So to answer this, we made an experiment with a hydrogen molecule, which has rather fast vibrational period. So it's good for this kind of investigation. It's relatively simple. So the vibrational period is 7.5 femtoseconds. And because we want to observe this in combination with this fast electronic dynamics, we chose like few cycle Titan sapphire laser pulse, which has duration of 4.5 femtosecond, and duration of one cycle is 2.5 femtosecond. So when such a short pulse interacts with a hydrogen, it ionizes that for the first time. Then the stretch motion happens on this cationic state H2+, which is called 1s sigma g. And after a certain time, second ionization can happen, which leaves behind only naked two protons that repel each other. And from this repulsion, you obtain some kinetic energy on the protons, which can be then measured in the experiment. And this kinetic energy, called also kinetic energy release, is a very good measure of the distance at what the second ionization step happened. So this is the relation. Kinetic energy release is the inverse, is approximately the inverse, proportional to the inverse of the distance. So here you have measure for the distance at the time of the second ionization step. But we are still missing the timing there, so we need to add there some time reference. And for this, we take our laser field, and we change our laser to a circularly polarized type, and we ionize in strong field regime, where the strong field approximation is valid. And this one has such a nice rule that the momentum of the emitted electrons is equal to the negative of the vector potential at the time of ionization. So the momentum of the electron is and the angle of the momentum is the time of the ionization. So it works as following. So at some certain time, you have a direction of your electric field vector. And at this time, the electron is ionized. And its final momentum will be given by the vector potential at this time. Later happens the second ionization step, for example, here quarter cycle after that, and this one will have different final momentum, this electron. So time or the delay between these two ionization steps is, you can read it from the angle of the electron. So this method is already well known, and it's called angular streaking. And now if we connect it with this kinetic energy release that we can observe for the molecules, we get a really powerful method for studying molecules. So there is certainly a lot of things to measure, a lot of momenta. So for this you need an appropriate apparatus. So here we used 3D momentum imaging apparatus called cold trims. This is such a spectrometer where you interact your gas beam with a laser beam. In the interacting region, the ions and electrons are released, and they are driven by the spectrometer field towards the position sensitive detector. And from the time of flight and the position on the detectors, then you get the momenta from the interaction. So for the interaction, such a few cycle laser pulse was used, which was also CEP carrier envelope phase tagged. So it means you have CEP information for every pulse. So now I will show you the results of such a measurement. Imagine you have such a case where you created these two protons by the double ionization. They receive some certain momenta that you measured in your experiment. You have two electrons emitted under certain angle. So the momentum of protons gives you the kinetic energy release and the distance when the second ionization step happened. And the angle between these two electrons then gives you the time that was taken between the first ionization step and the second ionization step. And now you can put these two observables together and plot a histogram of events. This one I show here. And on this vertical axis, you have this angle that covers one laser half cycle. And here, this is the kinetic energy release. Now how to read this histogram. So for this, we made quite a simple simulation where we propagated a quasi-particle on this cationic state of H2+, and we calculated the time and the kinetic energy release from the second ionization. And this makes such a parametric curve in this kinetic energy release and angle space. And this here comes the important part, that this parametric curve is characteristic for every pathway that leads to the final state. So if, for example, there would appear a process where this 2p sigma u state is occupied, that would lead to a different curve than here, and you would observe different distributions. So this is and as soon as your measurement is well coinciding with this prediction, you can really say that this is how the process of double ionization happened, that the molecule actually evolved on this 1s sigma g state. So I think that's quite an exciting conclusion of our observation. But we can go even further, and we can realize that if we limit ourselves to a very narrow interval of angles, we can receive attosecond snapshots of these nuclear wave packets. So this is what we did. We just selected very narrow interval of angles. And now I will show you how these profiles look. So here you have such a peak. Here is one peak hidden, and you can see here two peaks. So now if you realize the timing there, it means this blue one, it's how the wave packet looked like after half cycle of evolution. This is after one cycle of evolution, 1.5 cycle, and 2 cycles. After this point, we did some more sophisticated selection and some fittings, and we obtained the snapshots of this nuclear wave packet densities at this particular times, which are multiples of the half cycles. So you can imagine now we have like a camera that can make 100 attosecond exposure, and it has a rate half cycle of your laser pulse period. Yes, so I will conclude because now I can we can come back to this introductory graphics which illustrates these methods which I just presented. Here you have this circularly polarized laser field that gives you the temporal reference, which is projected into the angle of the electron emission. That gives then a kind of clock. And you, at the end, what you observe is motion of some certain potential energy surface where you can display the real densities or probability distribution of your nuclear wave packets. Now we can ask, can we apply it to larger molecules? And I can say, I think yes. There are good candidates, some molecules which have intrinsically fast dynamics. For example, hydrocarbons, that they have these CH bonds which can react quite fast to the ionization process. And we could even think about the extension of this method to some slower dynamics with using longer wavelength laser pulses. And now this brings me to the second part, where I will talk about identification of subcycle ionization bursts in double ionization. So I will still keep with the molecules, but one needs to realize that as soon as we are at the strong fields, at such intensities, we are in a tunnel ionization regime. And the tunnel ionization regime has such a characteristic that the rate of the ionization is depends exponentially on the electric field value, which creates very well localized bursts that have subcycle or attosecond duration. And because they are so sensitive, they are also sensitive to the waveform of the field, and you can then manipulate, or you can control these bursts of the ionization by controlling the waveform, for example, via Carrier envelope phase. And this gives you also control about the attosecond dynamics. So this was already studied in atoms, for example, in helium, where these subcycle bursts were identified in circularly polarized laser pulses, and it was shown that they can be controlled with the Carrier envelope phase. So now the question is how it works in molecules. So in molecules, we observed in our experiment that we do have subcycle ionization bursts there, and we were able to identify them. But we needed to use this kinetic energy release gating. So if we limit ourselves to this certain kinetic energy release, we know that that the electrons were emitted into the opposite directions, into the opposite hemispheres. So for example, the first electron went to the upper hemisphere, and then the second electron went to the lower hemisphere. So this, in turn, this we can visualize also in time. Here you have the ionization probability for the first electron, and one and a half cycle after that. We have here this ionization probability for the second electron. But this is our CEP integrated picture. So now if we limit ourselves just to one certain value of CEP, we can see that this ionization interval shrink to the subcycle duration, which we could call the subcycle burst. In this case, indeed, one electron was emitted towards the lower hemisphere, and the second electron was emitted towards the upper hemisphere in the laboratory frame. And this is given by the waveform of the laser, that it's like that. So here in this case, it's very important because you can distinguish the first emitted electron from the second emitted electron from the molecule, and you can separate them in your momentum space in the laboratory frame, which is not a trivial thing, and you cannot achieve it with the standard spectroscopic methods. If you go for another CEP, unfortunately, there is a subcycle bursts in 2 half cycles, which results in a mixed emission of electrons, and here you cannot distinguish first and second electron. No, and so because we are in molecules, it is important to study the electronic emission with respect to their orientation. And in our measurements, we were able to orient the molecules and do such a distinction of the electrons. So here I show you measured angular distribution of electrons, where indeed in the upper hemisphere it's just pure second emitted electron from the second ionization step, and in the lower hemisphere is just electron from the first ionization step. And this is important because as soon as you have such a separation, you can start to study the distribution, the momentum distribution of the second electron. And this can provide very important or useful information about the charge and electronic dynamics in this cation of a molecule, in this H2+, for example. And you receive access, you obtain access to attosecond electron emission and the dynamics in the molecules. So I would like to conclude the second part of my talk, and I would like to say that it is possible to use carrier envelope phase to disentangle subcycle electronic bursts from molecules. This gives access to attosecond electronic dynamics of singly ionized molecules, and an outlook for this method would be that you gain a possibility to trace the electronic wave packets of molecules after the ionization. So I thank you for your attention, and I would like to thank my colleague that helped a lot with this experiment, mostly Sareyu Kangaparambel and Sina Larimian, and my supervisor, Markus Kitzler.
So thank you very much for the nice talk. It was a very clear presentation. So I cannot see yet any questions on the chat, but I noticed that it takes a while to type them. So in the meanwhile, can you further explain the future prospect for the first technique? So you already mentioned that you are planning to apply it to more complex molecules that have carbon and hydrogen atoms. So which is the maximum length of the molecules that you can expect to study with this technique? Because I guess the more complex the molecule is, the more chance that it can interplay.
Well, certainly the transition to some other molecules, it's at this point, I think, quite challenging, and one needs to find a good working regime for it, like from the point of view of intensity and laser pulse shape, because it turned out that it is this hydrogen ionization was very sensitive to the laser pulse profile and so on. But to answer really your question about the bigger molecules, well, obviously, as you start, as you cross this, as you go for more complex molecules with more complicated electronic structure, also the potential energy landscape will be more complicated, and it can in fact reveal even much more structures in this space of this kinetic energy release and the electron emission angle. But at the end, one can, I think, discover plenty of new effects there, like maybe some interference and such. And I don't think that it's limited by bond length, but maybe it's limited really by the mass of the nuclei, because it should be like faster dynamics there.
Okay, I see. So I cannot see for the moment any other questions. Okay. So if there are no questions, just remember you can just write him on a private message or in the Meter hub. Otherwise, this was the last talk. And with this, I thank all the speakers of the session. And please remind that you must unlock from this session and log into the closing remarks session. So thank you very much for attending.